Okay, so this is the second part of our little lesson on the eye. So we finished off with sort of a general color blindness test that we were looking at, and now I want to look a little bit further at the genetics of color blindness. So I'll give you a little bit of information, and then I would like you to pause the video after I give you the information to try and solve some of this problem here. Okay, so color blindness is a recessive allele. The probability of males having color blindness is significantly higher than in females. So I want you to try and figure out why that might be. So I want you to draw the following pedigree. We'll say Jane is not colorblind and neither is her mom or dad. But Jane does have one older brother that is colorblind, so that her older brother is affected by color blindness. Okay, so I would like you to draw out that pedigree just to show that it's only 2 generations, 2 siblings, and that her older brother is colorblind. Then I would like you to say, what is the probability of Jane's mom and dad, if they were to have an additional child, what is the probability that the child would be colorblind? So at this point, I would like you to pause the video and just draw out a quick pedigree and a quick Punnett square, checking to see the probabilities. Okay, when you do this, I would like you to just check with someone else in the class to make sure you did get the same answers, and then you may continue on to the next slide. So pause the video now. Okay, so if you completed the pedigree, you would notice that you would have 3 individuals that were unaffected, single individual that was affected, and the probability that you may have found is that another child that was colorblind would be around 25%. Okay? Now, I'm going to ask you a different question that we maybe haven't talked about too much yet. And the question is what if that gene is carried on a sex chromosome? Now, the image I have posted on the slide here shows what we call a karyotype, which is essentially a gene map of all the genes in the human genome in their condensed chromosome form. So we have 23 pairs, as you can see, of chromosomes, making a total of 46, which is a human karyotype. And you can see that in general, we have a matching of height and sort of general shape or size of each of these pairs that we have. But you'll notice here at pair number 23, you'll see that there's sort of a large X and a smaller different chromosome. Now this is what we call a Y chromosome. So females carry an XX while males carry an XY chromosome pairing. So on the next slide, I have a little video that I would like you to watch to try and solve the same Punnett square that I asked you to solve in the previous question, but I want you to assume that color blindness is carried on a sex chromosome. So we'll watch the little video. The video isn't related to color blindness, but it is related to sex chromosomes. And I want you to watch the video and then see if you can apply what you learned in the video to your problem with color blindness. So let's take a look.
Would you like to know one of the most underappreciated pieces of cytoplasm out there? Platelets. We take for granted the function of our platelets, which are fragments of cytoplasm that help stop us from bleeding. They help our blood clot when we get hurt. But there is a disorder called hemophilia that can affect those platelets because special clotting factor proteins that are needed to work with the platelets may not work correctly. So even a basic cut could be dangerous for people with hemophilia because they could bleed continuously. We have many treatments for the symptoms of hemophilia, and this has greatly improved outcomes with this disorder. although it wasn't always that way. Hemophilia is a sex-linked recessive trait, which means it's different from the basic Mendelian genetic problems. What do I mean by that? Well, we still use the terms dominant and recessive for alleles, but this time, because it's sex-linked, the alleles are on sex chromosomes. This is the case with sex-linked traits. So what is a sex chromosome? Well, recall that humans have 46 chromosomes. Chromosomes are made up of DNA and protein, and they contain your genes. Well, 2 of your 46 chromosomes, they are called the sex chromosomes. In a karyotype, it is usually the last 2 chromosomes that are the sex chromosomes. The sex chromosomes are called X and Y chromosomes, but it has nothing to do with the shape of the chromosome. That's always kind of confusing, but please don't think that Y chromosomes are shaped like a Y and X chromosomes are shaped like an X. This used to always confuse me. It has nothing to do with their name. The reason they got their name is actually kind of interesting, so to the Google for that. Everyone has an X chromosome, but if you have another X chromosome, meaning you have 2 X chromosomes, you are female. And if you have a Y chromosome, meaning you have an X and a Y chromosome, you are male. There are also genetic disorders where you can have extra copies of sex chromosomes, but we will not go into that in this clip. Sex-linked traits are traits that are specifically on the sex chromosomes. Most sex-linked traits tend to be on the X chromosome because it is larger than the Y chromosome and it contains more genes in the Y chromosome. The disorder hemophilia is like this. Now we will use the letter capital H to represent an allele for having normal blood clotting function, and a letter lowercase h to represent an allele for having hemophilia. Hemophilia is a sex-linked recessive disorder, which is why it's being represented by a lowercase letter h. Only it must be placed on the sex chromosome as a superscript, like an exponent. A woman that does not have hemophilia could have the genotype X big H, X big H, or X big H, X little h. Because as long as she's got at least one dominant allele, that dominating allele will be what shows. So no hemophilia, since again, hemophilia is a recessive sex-linked disorder. The only way for her to have hemophilia would be the genotype X little h, because only when there is no dominant present will that recessive show up, at least in this type of trait. Now for a male to not have hemophilia, his genotype would have to be X big H, Y. Notice how I did not put anything on the Y chromosome. Again, most sex-linked traits are on the X chromosome. If he has the genotype X little h, Y, then he has hemophilia. He doesn't have 2 X chromosomes, so he cannot be a carrier. So let's say that 2 people that do not have hemophilia have children. However, let's say that the woman is a carrier. That means she is heterozygous. How do you do a sex-linked Punnett square cross for this kind of trait? Step 1. Identify the genotypes of the parents. So the mother was a carrier. She is X big H, X little h. She does not have hemophilia because of that dominant allele present, but she is a carrier. The male, if he does not have hemophilia, well, he must be X big H, Y. There's no other option for him. Step 2. Place one parent on the top, outside of the square like this, and place the other parent on the left, outside of the square like this. Step 3. Cross them. For formatting purposes, place X chromosomes before Y, and you also write any sex chromosomes with dominant letters first. The results you get in the squares would be the offspring, the babies. The genotype ratio could be written out like this. The phenotype ratio, remember that these are the observable traits, can be written out that there is a 75% chance that the child will be born without hemophilia and a 25% chance that a child would have hemophilia for this boy here. You could also make this a ratio, so 3 to 1. Notice that in this type of example of a sex-linked recessive disorder, males are more likely to inherit this disorder because there is only one X chromosome present. This is true for many other sex-linked recessive disorders, such as color blindness. Well, that's it for the Amoeba Sisters, and we remind you to stay curious.
Okay, so following that video, you should be able to create a Punnett square for the color blindness trait and get a little bit more information about what her family's genotypes are. So you should be able to map the genotypes, figure out what the genotypes are of all the individuals in the family, as well as look more at probabilities of if Jane's parents were to have another child, what the probability would be for that child to have color blindness. Okay, so again, remember that is more common in males. Now, the reason why color blindness is more common in males is we only get one X, and that X for sure comes from the mom. So the female has two X's, one coming from the dad and one coming from the mom. That gives two possibilities for there to be a dominant allele to mask the recessive allele that could possibly be present. Okay, so what I'm going to have you do now is you're going to collect a worksheet from the sub, and you're going to be filling out some additional information on visual defects. So your worksheet will look something like this, and you will have a little space here to fill out what the description of nearsightedness is, farsighted, astigmatism, cataract, glaucoma, as well as color blindness. Now, in terms of color blindness, I would like you to have some more information than what I covered in the presentation. So I'd like you to include, for example, different types of color blindness that might be and might exist in the world, as well as describing what color blindness is. Now, because of our society, we often have ways of correcting these things. So for example, with nearsightedness or farsightedness, we have corrective lenses such as glasses that you can put on your eyes in order to fix the image. So I would like you to describe the corrective technology that we have and how it works. So for example, this is just an example that if you are nearsighted, maybe you use a convex lens. How does that bend the light to correct that? Now, with that, again, from my, from my page here that I created for the lesson on the eye, you can click on this link here that's to the virtual eye. Now, this is a pretty cool little virtual eye that you can play around with. If you're just looking on the normal view, you can click on these tabs down here and you can get a little description of different parts of the eye. It will give you an option to select some different components and their labels. So this will say that this is the retina, and it will give a little bit of a description here. Okay, you can click on nearsightedness and farsightedness as well. And you can see by clicking on these buttons at the bottom how nearsightedness affects how light is bent in your eye and how light lands on your retina, and then how a corrective lens can help with that. The video explanation describes how corrective lenses work, and I would definitely recommend looking at that when you fill out your chart. Okay, this has nearsighted, farsighted, astigmatism. And for the other disorders that I've listed here, you may need to just do a little bit of research on Google to learn what, for example, what a cataract is and what glaucoma is to get some additional information to fill this out. You may work in groups to do this, but I would like each of you to have your own copy with this filled out by the end of class. Now, if you do end up finishing all of your worksheets there for the visual defects, you may go back to my webpage, watch these two videos that I have linked here, and if you finish that as well, I would like you to make a pedigree with 3 generations looking at the color blindness trait and how it is passed on through multiple generations. Okay, if you finish absolutely all of this, you've watched the videos and you've done some additional research maybe on some of the visual disorders, go talk to Fez to see what else you can do for this class to get ahead. All right, see you guys tomorrow.